Okay, question 7, the details. We already identified that this is going to be a two-tailed test, so we've identified specifically the null hypothesis that the long-term mean is equal to 211. That makes it a two-tailed test because we're dealing with an equal. Our confidence level equals 90%, which means our significance level is 1 minus the confidence level, and that is our significance level. So our significance level is 0.1, so 1 minus 90 is 0.1. It's a two-tailed test, so that means we're going to have 0.05. We'll actually use proper probability here and not just a 5. 0.05 over there and 0.05 over there. So the first thing that we need to do, we know our critical value identifies the rejection region, but we need to create an actual value or calculate an actual value for the critical value. Now, the critical value has nothing to do with our population mean, it has nothing to do with our sample mean, and then it has everything to do with how much probability we need in the wings. So that is the only thing the critical value does. It gives us our marker that tells us, that identifies where along this curve we need to put our threshold such that we have this probability left. We do that in this particular case because we have a t distribution that is two-tailed. We use the t.inv.2t function. If you remember, the .inv means we're going to give Excel a probability. So probability goes into the equation, and it will return to us a distance in standard error units. So remember, our distribution is based on sample means. So our distances are in standard errors. Now, if this was, instead of a population mean, if this was a sample mean, and the distribution was observations, then observation deviation, our distance would be in standard deviations. But no, we have a population mean here. Our sample is also a mean, so everything is in standard error units. As far as the critical value goes, it doesn't actually care what you're doing. It still just needs a probability, which is based on the tails, and a degrees of freedom. So the two-tailed function is a little bit backwards from how other Excel functions work. Even though we're interested, for instance, in this 0.05, we actually give it the full significance level. That's just a weird thing about the way Excel does it. And then it will divide that 0.1 into the two halves for us. So we give it the full significance level when we have the two-tailed version. We give it the degrees of freedom, which is n minus 1, n is the number of data, and then subtract 1. Note, this is the number of data, I just said number of data minus 1. And then it gives us a number. So this number is in standard error units. In our case, if this distribution was observations, the critical value would still be 2.92. Again, the critical value doesn't care if it's in standard deviation units or standard error units, because all we're giving it is a probability. And the shape of the curve does not change if we're talking about standard deviations or standard errors. It's still a t distribution. So 2.92 is our distance, and we just have to know that it is a distance in standard error units. So this is saying that the critical value, this particular threshold, is 2.92 standard errors. And that means we have 1 standard error, 2 standard error, I made that a little bit large, 2.92 standard errors over here. And we would also go 1, 2, almost 3, 2.92 to get over here. So we only have one value, but because we're dealing with two-tailed tests, there are two critical values, and one of them is negative. So here's our critical value, 2.92. That identifies our threshold. So if our sample mean, so our sample mean right now is in megatons CO2 in a year, original data units. Our distribution, like our critical value, is in standard error units. So we need to take our sample mean and convert that somehow into standard error units. Ultimately, once we do that, we will put another line that represents our sample mean, And if that sample mean is in this purple area, then we fail to reject the null hypothesis. And if the sample mean falls in the rejection region, then we will reject the null hypothesis. So we've set up our regions. That's what the critical value does for us. We then need to do this conversion. So this conversion from original data units into standard errors or standard deviations, depending, but for us it's standard errors. That's what the t-score is. So if we look at the equation, looks like I just have the numbers here. We take the sample mean minus the population mean. So that's the kind of change in original units. And then we do our unit conversion by dividing by the standard error. I have the standard error calculated up here. Remember, the standard error is the standard deviation divided by the square root of n. That's an n. Note that this n are the number of data in the data set. It's not the degrees of freedom, so we don't subtract 1 from this n. This is the actual number of data points. So this formula gave us the standard error, and then the standard error went into the t-score as part of our conversion from sample mean into standard error units. So we have our critical value. Our t-score says, well, our critical value over here was minus, and for this one, minus 2.92. Our data are minus 5.5. So our critical value was about 3 hops. Now we're going 1, 2, 3, 4, 5 hops away. So that is where our sample resides in standard error units. Now, remember that if we cross into the green region, we are going to reject the null hypothesis. This is our rejection region. So our data in standard error units is more extreme than the critical value, which just means we've gone into the green region. So yes, we will very readily reject the null hypothesis. So that's our first method of doing it. So we've calculated our critical value. We've compared that to the t-score. Our second way of doing this is with p-values, and I'm just going to make that next video.